Joy Altweis is a program director for the UW-Madison Office of Interdisciplinary Professional Programs. And she's developed and taught continuing education courses emphasizing high performance building design and construction, mechanical system design and operation, energy efficiency, and commissioning. And she's also program director of the Master's of Sustainable Systems Engineering degree program, which we have students, as I mentioned, in the program. And she teaches 2 graduate courses in that program as well. So welcome, Joy.
Thank you. Glad to be here. I apologize that I can't be there in person, but trust me, you don't want me there in person today. So I will do my best and we will get through this, and hopefully you'll gain some information about decarbonizing buildings for a sustainable energy future. All right, so I'm just going to dive right in, and thank you, Scott, for the introduction. I'll kind of build on that a little bit to introduce myself a little bit more. I'm a program director in interdisciplinary professional programs, as Scott mentioned, and my role is actually in 2 parts. I have requirements that I run the Sustainable Systems Engineering online master's degree, and then I'm also about 50% on our non-credit courses as well. So I do courses pretty much all year round, a lot of them over at the Pyle Center on campus, in case any of you have been there, where practicing engineers come back to campus for a short topic, usually 2 to 3, sometimes 5 days long. And so that's a little bit about me and my background. I'm a mechanical engineer. I have a bachelor's and a master's degree in mechanical engineering, and my specialty area is buildings and building systems, and along with that, sustainability in buildings. So that's what we're going to talk about today. All right, so I kind of divided today's session into 2 parts. So the part 1 is the big picture. So why do we care about buildings? What's the deal? Why does this matter in the big picture? So we'll talk about how buildings contribute to carbon emissions and what are some of the current trends in both commercial and residential buildings. In the second part, we'll move into, can we improve these buildings? Are there things that we can do to make them more efficient and consume less energy and less carbon? So we'll look at what consumes energy in buildings and strategies to reduce that energy consumption. And we'll then talk a little bit about decarbonization, because that's kind of the trend that's really prevalent in the industry right now, talking about decarbonizing our buildings. And so I'm actually going to start with that first. So let's talk about that. So let's go into the big picture. Carbon emissions and energy use in buildings today. So terminology, I said we're going to start with that. So I'm going to flip it around. Do we talk about carbon, or do we talk about energy? And in most places, at least in the US, if you lower your energy use, then you are going to be lowering your carbon emissions. And that's true in most places. I've got a couple of slides coming up, and we'll talk about why that is. So of course it has to do with, if you're using energy most of the time, that's some sort of a carbon emitting source of energy, usually fossil fuels. But we'll talk about that in a couple of slides. Now, can we decarbonize our buildings, and what do we mean by that? So when we talk about decarbonization, we need to look at the full life cycle of our buildings, from when we build them through all the years of operation until we are done with them and we tear them down or reconstruct them or deconstruct them into another purpose. So we have to think about 2 aspects of decarbonization. So there's carbon emissions in our buildings in terms of embodied carbon. So when we construct the buildings, all the materials that go into the building itself, there's embodied carbon in that phase of its life. But all the years you're operating a building, whether it's your home or a commercial building, there's operational carbon, which means we're using energy all those years to run the buildings, to keep ourselves warm and cool, to run the lights. So both the embodied carbon and the operational carbon are very important. And we're going to talk a little bit more in this talk about the operational carbon. That's usually where the engineers come in, talking about how do we use energy more efficiently in the day-to-day operation of a building. The embodied carbon tends to be more on the designers of the buildings, the architects, the folks who are selecting materials to go into our buildings. So I just want you to be aware of both aspects of the life cycle of buildings and how there's carbon in both. But in this talk, we're going to be a little bit more focused on the operational side of the carbon. So what do I mean by that? Well, if we're using electricity, more than likely we are emitting carbon. Many of you may know this. This might be new information, I'm not sure, depending on your background. But the amount of carbon that gets released into the atmosphere when you use electricity is dependent on what area you live in. Some electric grids are more carbon intensive than others. It depends on the source of that electricity. So our top 4 states for the lowest carbon in their grid are Vermont, Washington, Idaho, and South Dakota. Vermont and Washington have a lot of hydroelectric, so they have a source of electricity that is low carbon intensive. I believe that may be true of Idaho as well. South Dakota, I believe, is a lot of wind power. On the other side, we have the highest carbon grid. And these states are the ones that have the most fossil fuel intensive electricity. And just a little note there on the bottom, Wisconsin is number 43 out of 52, which means our grid here in Wisconsin is fairly carbon heavy still. We're making progress, and this is a snapshot in time. This is the most recent data they have on eGrid from 2021. There's 52 items on the list, or 52 locations on the list, because they include Puerto Rico and Washington, D.C. So Wisconsin is still a fairly carbon intensive grid, which means if you are looking at ways to improve your buildings and you're in one of the more carbon intensive grid areas, if you go to electricity, chances are you're actually not making not making it better yet. There will be a time, hopefully soon, when we are able to decarbonize the electric grid even more. And in that case, we will be able to move to more electric-based sources of energy without creating more carbon. So just want to give you kind of a background here on where the carbon comes from and how carbon intensive our electric grid is. Now, where does this come from? Well, in 2020, this is an interesting map. I don't know if you can see some of these colors. The size of the circle is the size of the power plant. So you can see one of them that stands out here is the blue one up in the Pacific Northwest. That is a very large hydroelectric plant. So you can see why Washington State and Idaho have a fairly low carbon grid. The gray circles tend to be the fossil and coal plants. And you can see there's pockets of red. Those are solar farms. They're usually really tiny. They're small individual solar plants. But altogether, they are contributing. So I just wanted to give you kind of a background of where our power is coming from currently. And this is from 2020. All right, so let's talk about buildings. So I give you a little background on the electric grid and where we're getting our energy from. So if you're in a building, you're using either fuels on site, such as natural gas, right in your furnace, in your home furnace, or you're using electricity. And so let's take a look at the US energy flow. So they do one of these flow diagrams every year. And you can see the sources. Let's see if I can pull up the annotation here. Yeah, can you see my pointer there? I think you can.
Yeah, I can see your dot.
Great. So over here, you can see the sources. You've got coal and natural gas, and the size of the incoming stream is, of course, the proportion of that source. And then on the other side, we have where all this energy is going. So essentially, sources on the left and users on the right. And so on the right, you have 4 main sectors of the economy in terms of energy users. And we're going to talk about those top 2, the residential and commercial buildings. So together, they make about 38% of the overall use of our energy. Now, this is an interesting chart, and I mentioned that they have one of these every year. This comes from the Energy Information Administration. And just for a comparison, here's the 2002 version. So if you go back 20 years, I think. There's a few things that you might notice. One is that the residential and commercial proportion hasn't changed that much, still around 38% of the total energy uses. It's much more interesting looking at the sources. So the amount of coal is much higher back in 2002. The amount of natural gas is much lower. If you remember the previous slide, this piece was much skinnier and the natural gas piece was much wider. So I just wanted to give you a reference point for 20 years. Things are changing, but not as much in the area we're going to talk about, which is the commercial and residential. So I said we have 4 sectors of US energy users. And we're going to talk about residential and commercial. I'm not going to talk about the transportation sector or the industrial sector in this talk. Not really my area. So we have 38%, I mentioned that before, used by various types of buildings. So when we talk about commercial buildings, we're talking about, your office buildings, your retail, your fast food, hospitals, just any type of building which is not a residential building, but it's also not an industrial facility. And then of course, residential is any place where people live. So apartments, multifamily, single family homes. So why does this matter? Well, in the big picture, in order to switch to a green and decarbonized economy, we need to reduce our consumption. Why? Well, because we have to shift to renewable sources of power. And that's a transition that's going to take a while, and it's going to take even longer if we're continually consuming more and more energy. So this gives you a picture of residential and commercial, the green and blue lines. And you notice the last 20 years or so, how flat they are. Remember, I showed you the 2002 versus the 2022. Hasn't changed that much, about 38%. So that's actually fairly impressive considering how many homes and buildings have been built in that amount of time. So we're actually holding the line steady, but unfortunately we need to reduce the line. We need to drop the line and not just hold it steady. So consumption is really important. It's not as exciting as, wind power and solar power, but it's certainly critical in terms of our long-term decarbonization of the economy. So yeah, buildings are drivers of current and future sustainability. So in terms of retail electricity, buildings consume 73%. So that is not a small amount. I mentioned the 38% of the primary energy use. And something that's kind of easy to forget with our buildings, 94% of our buildings are already here. They're already built, they're existing buildings. And in any given year, somewhere around 5 to 6% are new buildings being built. So it takes a long time to replace the full building stock. And that's based on the 2018 Commercial Building Energy Consumption Survey data. So it's important to remember for those of us who are in the building and construction industry, we get really excited about new buildings being built and all the cool things we can do with them, and getting LEED credits and all kinds of things that we can do with new construction. But that's really not, I mean, it helps. This is certainly good to do, but the real key here is that we've got to bring the consumption down in our existing building stock as well, because that's the vast majority of the buildings that we have. So improving energy efficiency is crucial. It can be considered a resource, if you will, to avoid new power generation. So since 1990, it is actually the 3rd largest electricity resource in the US. And what does that mean? Well, that means if we didn't do anything in terms of energy efficiency, if we just, used old-fashioned inefficient light bulbs, and we didn't care how efficient our furnaces and heating and cooling was, and we did nothing in terms of keeping our buildings efficient, we would need 313 more power plants right now just to power all those buildings. So efficiency really is crucial. So energy efficiency, how does this fit into the overall plan to limit climate change? Well, it's a major part. If you look at it in this scenario here, this goes from 2010 to 2040. And these are all the various pieces and parts that are going to help us get to our climate goals. And, notice the biggest piece of that is energy efficiency, that big green wedge at the top. And so that's to get us to stick to the 2-degree scenario. And all of those things matter, of course, and you can see how big a piece of the pie the renewables are as well. But yeah, energy efficiency is huge. It's a major piece of it. So how are we doing? Well, it's a mixed bag. Um, Emissions overall from the building sector are not decreasing, not yet. They're holding steady. Um, when you look at it in terms of energy use per square foot, we're actually doing pretty well because, again, we keep building more buildings, but we're not actually bending the line down yet. So we're still growing, unfortunately, our energy use in the building sector. So we have some challenges that we're facing. One of them is the fact that we do keep building more buildings, and so we expect to double our building stock, our floor space, by 2050. Uh, and the trend isn't exactly going in the right direction. We are emitting more from the building sector than we were in 2015. We did have a dip during the pandemic, of course, but it popped right back up in the last 2 years. And based on, there's a new report coming out from UNEP and IEA, and it's actually coming out next month. It's the preview, it's the 2023 Global Status Report. And based on what they're saying, unfortunately, buildings are not yet on track to meet our climate goals. So we do have some challenges in front of us. So I sort of set the stage for you in terms of how much does energy efficiency matter? How much do buildings matter in the big picture? So let's talk about, can we improve energy efficiency in our buildings? And again, that goes hand in hand with decarbonizing, especially in the operational phase, especially if you're in one of those areas where your electricity usage is fairly carbon intensive. So can we improve the energy efficiency? Big answer, short answer, yes, of course we can. And we've shown that we can do it. So this is our energy use per square foot in commercial buildings from 1979 through 2018. And you can see it's going down. Yay! So when you do look at it on a per square foot basis, of course, it's going down. We've been building more buildings and we've holding that consumption line steady, which means as a unit of energy per square foot, we're actually going down, which is good. And you can see both electricity and natural gas underneath. So we are making some progress, and this is in the commercial building area. Same thing in the residential. Can we do it? Absolutely. There is data behind it. So as we've been growing the number of housing units, and that's the blue dotted line, we've still been dropping our average consumption per household, which is great. We're doing wonderful. That's amazing, because if we hadn't been doing anything with energy efficiency, those lines would be moving together. So we are making good headway. It's just that overall, we're still using more than we had in the past. And this is data that's coming from the EIA as well. So what makes a building a good building or a bad building? There's no good buildings, there's no bad buildings. It's just some of them are energy champs and some of them are, well, energy hogs. And what determines the difference? So where does the energy go in our buildings? So we'll talk about first building heat gains and losses. So heat goes out through your envelope, your walls, your windows, your insulation, and what determines whether that is a good amount of energy loss or an excessive amount of energy loss? Well, uh, in most places, we have what we call building codes, which are rules that we have to follow. They're laws that specify you have to do at least this much in terms of your window efficiency, the amount of insulation in your walls, and things like the amount of windows per unit space of wall. So, like if you built an entirely glass house, that probably wouldn't meet code. So there's a lot that goes into determining just the envelope itself, how efficient it is. Inside the building, there's things using energy, of course. So imagine your own home. You've got lights, you've got appliances, and there's lots of choices with all of those. You can buy inefficient lights. You can buy, super efficient LEDs. Same thing with your appliances. You've probably heard of Energy Star refrigerators and washing machines. So there are certainly better choices that we can make in terms of our indoor internal gains. And then ventilation. How much outdoor air do we have to bring in to make sure people are healthy? This you don't hear about this quite as much with residential, but certainly in commercial buildings, there are codes again that require you to bring in a certain amount of outside air to ventilate the space to make sure people are healthy. And usually that's a bit of an energy penalty, especially in Wisconsin where it's cold a lot of the year. So you got to heat that and you got to heat that air up, but you have to do it anyway because otherwise, you can't seal people in; they'd get sick. So let's take a look at an example. So this is my area. This is heating, ventilating, and air conditioning, HVAC. Here's a basic residential. So imagine a single family home. You've got a furnace in this situation. There's lots of different ways to heat and cool homes, but this is a simple um, heating coil inside of this would be like a natural gas furnace. It's got a fan in there. It blows the air across the heating coil from the, let's say, a natural gas burner. And this would be in the wintertime. The cooling coils would not be doing anything. They'd just be sitting there. And then it blows that air throughout the home into all the different rooms with supply air. And then, of course, it's controlled by a thermostat, which tells it whether or not to turn on or off. And in the summer, the heating coil would be silent, quiet, and the compressor on the outside would be working, sending cool refrigerant into those cooling coils and sending cool air throughout the house. So this is a basic um, residential HVAC system, and you can see there's lots of things here that use energy. That fan in particular, that is blowing air throughout the home. The heating coils, that heat has to come from somewhere, usually natural gas or propane. And then, of course, the air conditioning. So those cooling coils, to make that refrigerant cool, you have the equipment on the outside of the house that's run by electricity. So lots of different ways that HVAC is using energy here. Here we have a commercial version. So it's basically the same thing, it's just a lot more complicated. So here, this is the summer version. This is outside. You have hot air outside. And remember, I said codes require that you have to bring in ventilation air for health reasons. So you have to bring some of that hot air in. And then, of course, you're blowing it across coils that are cooling it down. And those coils are fed by a refrigerant, usually, or cold water, which also requires energy to do. And then, of course, the fans, and in this case, the heating coil will be quiet because it's in the middle of summer. And that's all supplied into the individual rooms. And then, of course, the air returns back, and some of it is exhausted outside, and some of it is returned through the system. And in the winter, when it's cold outside, your cooling coil shuts off, and now you're using your heating coil. And again, the heating coil could be electricity, like electric resistance heat, but not usually. It's usually being provided by a boiler, which is running hot water to those coils, and the air is blowing across them to heat up the air, which is supplied to the space. And that's pretty basic explanation of HVAC and where some of the energy is going. But you can see there's lots of spots there in that system, just in that system alone, that are using energy, either directly by burning fossil fuels or by electricity coming from the grid. So that's heating and cooling losses. Now, I mentioned equipment and appliance choices. Things like choosing Energy Star items, the efficiency rating on your furnace. Those are all things that are going to determine how much energy is being used by the appliances and the equipment that you choose. And don't forget, there's also something called plug loads, and we've probably all familiar with this. So plug loads are anything you plug in, basically. If you've got outlets throughout your house, anything you plug in is a plug load. Sometimes they're called energy vampires if they're running all the time, even though you're not using it. Certain entertainment equipment tends to be energy vampires, using a lot of energy even when you don't have it turned on. And then finally, there's a big area of control strategies and user behavior. And this is one of the areas where some of the working engineers come back for their short courses to learn better control strategies. It's one of the ones I run. Things like, you know, setting equipment to unoccupied mode. What does that mean? Well, if there's nobody in the building, let's say it's 3 a.m., you don't need to be keeping it perfect, comfortable, 72 degrees. You can let that float to a less comfortable temperature because there's nobody in the building. So there's modes like that. There's automatic lighting that comes on and off based on daylight or time of day. There's ways you can use free cooling. Certain times of the year, the outside air is absolutely perfect the way it is. So can you program the equipment to just blow all outdoor air in instead of trying to heat and cool? Yes, you can. That's called free cooling, and that's an option as long as you program it into the system. So there's lots of opportunities to do things right, to make buildings really efficient, and lots of opportunities to mess them up, to make them do really stupid. It's usually not done on purpose, but inefficient ways of doing things. And I mentioned their user behavior. That's a whole field of study in and of itself. How people interact with the systems, like in your home, how you interact with your thermostat. In commercial buildings, do people remember to turn off the lights when they leave a room, or do you need to do automatic shutoffs? So user behavior is a big part of it as well. And sometimes, depending on the building, can be the major driver of whether a building is an energy champ or an energy hog. So what's a strategy that we can follow? Well, there's a few ways to improve energy efficiency in any building. And the first one is always to reduce the loads. And the loads I'm talking about are, how much insulation, so how much heat is coming in through the outside, how much are the lights putting out, so you can use daylighting to reduce those loads that are brought into the building that need to be heated or cooled. The second way is, of course, to choose high efficiency equipment. So making the choice to use a higher efficiency furnace or a high efficiency refrigerator in a home. Just making that simple choice can have a huge long-term impact. And then, of course, number 3 is always to take advantage of any free energy sources that may be available. So the 3 here are all commercial building examples. So waste heat recovery, for example, maybe you have one area of your commercial building where there's excess energy. Maybe it's a computer lab room and there's a lot of energy, a lot of heat in that room naturally. You can capture that heat and use it in another part of the building that needs it. Perhaps maybe some offices by windows during the wintertime. There's ways to do that, and it's free heat, so why not, right? Um, Economizers, that's bringing in the outside air when it's at the perfect condition, and not wasting energy heating and cooling air when you can have free air from outside. Night pre-cooling is another one. Sometimes you can take advantage of no one's in the building at night, so you could pre-cool that building so that on a hot summer day, you don't have to use as much mechanical cooling to keep the building comfortable throughout the day. So these are just some examples of some strategies. Daylighting is another big one. So here I've got a few pictures for you of, this is a real building here in Wisconsin. It's up in Green Bay. And I'll show you here the south face of the building and the north face of the building. So what is daylighting? Well, it's taking advantage of as much free daylight from outside as possible so that you don't have to use as many lights indoors. This is going to save you both electric lighting energy and potentially that heat load that you're not, because you're not running the lights, there's less heat being given off. This is the south facing wall. I'll turn on my spotlight again. So this faces south, and you can see there's a large overhang on the outside of the building. The reason they do this is so that during the summer months, when the sun is very high in the sky, this provides shading on these windows. In the winter months, when the sun is lower, you get more of the direct sun coming into those windows. So it's a strategy to take advantage of the position of the sun as it changes through the year. On the inside of that same wall, so this is the inside of that picture, you can see they have these shelves. They call them light shelves above the windows. And this does a couple things. That you notice it's white on the top. This helps to bounce the light that's coming in from the upper windows onto this light colored surface and back up onto the ceiling. And this will help spread the light further into the interior of the building and help to reduce the need for electric light. At the same time, you have view windows underneath so people can see directly out outside of the building. All right. And this is the same building, but facing north. This is the opposite side of the building. And you notice there's no overhangs now. There's nothing blocking any of these windows. That's because obviously in the northern hemisphere, you're never going to have, at least most of the time, you're not going to have any direct sun throughout the year. So you want to take advantage of as much of that light as you possibly can, because it's always going to be diffuse light. It's never going to be direct glare. And you can see again, this is the inside of the building down here. And again, they're trying to use as much of that light as they possibly can to get it as far into the floor plate as possible. It's just a really efficient strategy. Of course, it has to be designed in from the beginning. It's a little bit difficult to do to an existing building that wasn't designed for it, but it's a great strategy for a new building. So this particular building up in Green Bay is interesting because this is a building, it's a state-owned building, and they decided they were going to try to be as efficient as they possibly could in the design of this building. And they actually went for a LEED rating, if you're familiar with LEED. And I want to draw your attention to this chart here. So you can see here the column, that first tall column, says if they built this building to code. So Wisconsin has a building code, and if they had built it to the base level required by code for energy efficiency, that's how much energy it would have used. But they didn't do that. They decided they were going to make it much more efficient than code. So they ran, when they were doing the design, they ran some models, energy models, and there's software programs to do this. I actually teach a class on running energy models for buildings. And the computer model showed that with all their special design features, like their daylighting and all that stuff, they predicted they were gonna use 50% less energy than if they had just built to code. And what's even more interesting is the last column. So the last column is the building, the real building, after it was finished and in operation. And it shows that they did even better than they thought they were going to do. Their building meter showed actually a 57% energy savings compared to the code. So great things are possible here. They were so pleased with this building that it did so well compared to even what they were expecting, which is exciting. I did mention they achieved a few other notable things with this particular project. They got a LEED Gold. So LEED is the green building rating system, and it's run by the U.S. Green Building Council. And so they were able to, they were aiming to get a LEED Silver, which is like the second level, and they actually got to Gold, which is the third level from the top. Their construction costs, this may or may not mean anything to you, but $108 a square foot is actually really reasonable. It's not crazy at all, especially for the time. And so they weren't doing anything particularly unusual. They were using no high-tech stuff. They were just using off-the-shelf types of systems. They just did a really good job of designing it and keeping to their budget. So it can be done. And they're, like I said on the previous slide, the real world savings they've been seeing are just phenomenal. They're even better than they were expecting. So it's not impossible. It doesn't have to be expensive. You don't have to use bleeding edge technology or equipment. It just, if you design it in from the beginning, it can be done. And this is a great example here, just, in our own backyard here in Wisconsin. So I'll leave you with this thought. Great things are possible. Um, how? Well, I would say the future really is zero carbon, and that's where all the conversation right now has been, with the future of buildings, is trying to decarbonize both in the embodied carbon initial construction phase and during that operational lifetime carbon. So how do we do it? I recommend always to encourage change through policy. Um, how? Well, you can incentivize building owners and building designers to do things. For example, they usually respond really well to, for example, fast tracking permits if they design a very energy efficient building. Um, you can reward it, for example, by giving out financial incentives like rebates for energy efficiency. In fact, there was a very large law passed last year, the IRA, some of you may be familiar with, that does exactly that. And you can, those are kind of the carrots, if you will, the carrot approaches, but you can also take the stick and whack people with the stick and say, you have to do this. How do you do that? By mandating it through stricter building codes. The building code can be updated and made more stringent over time, and it should be. And that will bring up everybody, even the ones who are a bit reluctant to do so. And then moving towards net zero energy and net zero carbon, you don't have to just stop there. You can try to make your building zero energy and then go further, put PVs on the building, produce power, send it back to the grid, become a producer of green power. You can focus on the full life cycle carbon. I mentioned that before. My industry, the area I work in, the HVAC engineers out there, we've been focusing on operational carbon for a long time, mostly just through energy efficiency. But we're getting to the point where we need to go beyond that. We need to look at the entire embodied carbon in our systems. And so we're moving in that direction now. And the last thing I'll note is emphasize existing building improvements. I noted earlier in the slides that most of our buildings are already built. And we do slowly replace them, but the turnover is 5-6% a year. So it does take time to bring in all new buildings. And of course, not all new buildings are being built super efficient either. So we need to really emphasize making our buildings more efficient, our existing buildings, and finding ways to improve existing buildings, reuse existing buildings. For those of you who are in the class, I gave you a few optional readings as well, and one of them was an amazing reuse of an existing building here in Wisconsin in Beloit. So if you happen to read that one, it's pretty impressive. So just wanted to give you that example of reuse of an existing structure. All right, that's what I have for you. I've left time for questions. Hooray! I wasn't sure if I was going to, but I did.
Great, thanks, Joy. And I'm going to try to turn on the camera in here in the room so you can see the folks that are in the room if we have any questions. So I'll note that you might see the camera pop up in just a second here. All right. right. I think we got any questions from folks here in the room?
Thank you for an excellent talk, Joy. Can you hear me?
Sure.
Okay.
Yeah. Hi.
Excellent. Hi. I'm curious what strategies UW is planning to follow to improve energy efficiency on campus, both in the existing buildings and all of the new buildings that are being built to achieve net zero. And I believe electricity energy, and I believe that's by 2050 is the campus goal, although I might be
I
wrong
think it
about
was like
that.
2048 or something.
2048.
Yeah.
Yeah.
That's
Thank
a
you.
great. Sure, thanks. That's a great question for the Office of Sustainability. We do have an Office of Sustainability on campus and also the Office of Facility Planning and Management. And I know they're doing a lot of things. They have folks in FP&M that are focused on this exact thing. I know that with the new buildings, they're focusing on trying to get LEED for one thing. I know the new computer sciences building that's being built across the way over there is got a lot of amazing features, and they have activities going on all the time in our buildings. And in terms of improving the existing buildings that we have, if you haven't already, I highly encourage you to check out the Office of Sustainability's website, because they have all their activities going on, not just the building related ones, but everything going on campus, and what they're trying to work on. The buildings, it's a tough one. I think we're doing the best we can with it, but we have to be careful. Some buildings on campus have very critical labs and experiments and things going on that we have to be careful with, but it can be done, and I think we're moving in that direction fairly quickly. I'm always excited to see, like, when we put up new dorms, and for example, on uh, the other end of campus, with the solar panels and everything on it, and the buildings that have the dashboards in them where you can walk in and see, the performance. Those are always exciting. Um, yeah, because it's important. We have our own power plants on campus where we're Charter Street and everything, where we're actually, burning burning energy, and so it's important to try to keep that energy use down. So I think we're making some progress. But Scott, you should have somebody from FP&M come over and give a talk on what exactly they're doing.
Sure. Thank you. We've got a couple of questions online. And first, address the one in the Q&A. So Sandy was asking, how has COVID added to the challenge of building indoor air quality, especially for a life cycle assessment perspective?
Yeah, it's been challenging for certain. COVID shifted the focus, obviously, for very good reason. Up until the pandemic hit, we've been focusing on energy efficiency, sustainability, and then all of a sudden, as an industry, my industry, ASHRAE, we completely turned towards indoor environmental quality for good reason. We've had to focus more on making sure that whatever we do, we are not jeopardizing the health and safety of people inside. And that's always been a focus, but not like it is now. The amount of filtration, the maintenance, and how things are how often filters are changed and maintained, because I think it was made very clear to us as an industry that that's not optional. We can't we can't fool ourselves into believing that that'll never happen. I think we've all lived through that now. So yeah, it's made it more challenging. Energy efficiency and indoor air quality have historically been two sides of the same coin. We want to ventilate, we want to provide a healthy environment, but our traditional systems have meant that uses more energy. And it doesn't have to, but it has to be done carefully and designed well so that you can accomplish both goals at the same time. But yeah, the last few years have certainly been interesting in the HVAC world, that's for sure. So a bit frustrating in the beginning of COVID because folks in my industry kind of knew based on some of the data we were seeing, how COVID was spreading, and we couldn't get much attention from the powers that be to address it. So lesson learned, I guess.
Great, thanks. Another question online was, how do you feel about solar panels in comparison to green or blue roofs in terms of their carbon footprint or buildings' carbon footprint?
Oh yeah, solar panels. If I had the choice, I'd do both. So if I had some yard, I'd put the solar panels in the yard, and I'd do green roof on the top of the building. So green roof, you're talking about a vegetated roof. Ideally, someplace that is also serves as a place of respite, a place of where people can go out and sit and enjoy the garden, if you will. I'm assuming that's what you're referring to. I would love to do both. But again, a lot of buildings don't have, yard space. So it's a trade-off. In some cases, they don't want people going on the roof, I guess. Maybe it's not accessible, maybe there's not an elevator, and that's okay. It's just a matter of, you know, some building owners have their preferences. They either want to show off the PV and the investment in the renewables, or they want to have, a pleasant, nice space for, their occupants. They're both great goals. Like I said, I would love to see both. Um, you don't always get that, but it's always, personally, I love green roofs. I think they're fun and exciting. I'm a gardener, so that's my thing. But
I guess what about the insulation value of that?
yeah,
Sort of the trade-offs with that.
yeah. So a green roof, depending on the thickness and whether it's intensive or extensive, determines how thick the growing medium needs to be on the roof. And so there's design factors in terms of whether that medium is wet or dry, and thermal conductivity through it. But in general, it's an insulator, I believe. And similarly with PV, you get the shading effect. So you'd have shading on the roof surface. Now there's trade-offs there as well for eventual roof material replacement. My expectation is that with a PV roof, you would have a longer life of your roofing material, just because you're not getting the solar directly on it. So there's lots of factors to consider in terms of which option is the most appropriate for a particular owner in a particular situation.
Great, thanks. And then a question came in from James. Are you seeing more use of geothermal in HVAC systems? And we actually had a speaker, Jim Tinjum, speak, I think in the last semester, talking also about kind of district scale geothermal systems where you're connecting more than one building, and how EPIC has been able to accomplish that.
Yes, definitely. Geothermal is a great option. Why? Because it allows you to use to electrify, essentially, to not burn the fossil fuel directly. So you get rid of your scope 1 emissions. Geothermal is great because we have the ground source, the sink, the heat source and sink in the ground, which is that constant temperature year round. And the equipment, I believe, that we have for geothermal is a little bit more advanced. We're getting there really quickly with air source heat pumps as well. That's where a lot of emphasis is being put right now in terms of getting air source heat pumps up to usability in a climate even as extreme as ours. But geothermal is a fantastic system. It's a little more expensive on the initial installation, but yeah, to see it going to district scale, and it's very exciting. It's exciting to me. This is sort of stuff I've kind of imagined my whole career as being possible, and to see it actually happening is exciting.
Thanks. Any other questions in the room? You can use it. Yep.
Is this live?
It should be, yeah.
Can you hear me?
Yep.
Coming from a viewpoint of a homeowner, there's a lot of improvement to be made And I was just reading an article today by, it was actually INREL, how we're going to convert energy use at home in the future to go all electric. And part of that is going likely to require the use of heat pumps. On the one hand, they're expensive. And on the other, they're going to use electricity, and the cost of electrical energy relative to gas is fairly high. And the elephant in the room to me is how we're going to convert the installed base of existing homes to, let's just say, the future, where we're going to have to make substantial reductions in our carbon footprint. I'm sorry, that's half a question and half a statement.
Half a question, half a statement. Yeah.
I can't discern what the solution is going to be to this yet.
Probably a gradual one. We can't just go all electric right now because it would be extremely expensive. Our electric and gas utility pricing structure in this country is designed around, well, there's a lot to it, but in a lot of places, the electric is more expensive for a lot of reasons. We need to make sure we're not just falling back on electric resistance heating, because it will just drive people into bankruptcy, especially lower income people. They simply can't afford that. So as we develop and get better and better with some of these heat pump technologies, I think it'll be a gradual transition. And frankly, right now, we don't have the technicians yet. We're working on it to know the best application, the best design for each home. But I have a feeling it'll be a gradual changeover over time. As people's furnaces wear out and they need new ones. That's my hope.
And actually, we have some research that's been done on campus through Professor Morgan Edwards that looked at kind of statewide across Wisconsin, which localities might be better suited to switch over, if they're using propane already or other kind of high costs. If they're already using electric resistance heat, that those might be the places to start in terms of transitioning over.
Yeah. And keep in mind also that propane and natural gas aren't the dirtiest fuels. I mean, they're still fossil fuels, but they're not the dirtiest ones. So I think a gradual shift off of the really dirty fuels is probably the best move. And like I said at the beginning of this talk, there's not really any point right now in, for example, electrifying every home in Wisconsin, because you'd actually be making it worse. Because our grid is still fairly dirty. As that shifts and changes, and it will over time as we get more renewables on the grid, then yeah. But I think it's going to be a transition over a number of years.
Great, thanks. Got a couple more questions online. One from Zoe is wondering if you've heard of solar panel windows and whether they're realistic.
Yes, I have heard of solar panel windows. In fact, I've seen solar facades as well at the U.S. Green Building Council conference. They have vendors there doing trade show stuff, and they have not just windows, but like materials for siding and all kinds of things that have PV built into them. Really exciting stuff. Right now, still a little on the expensive side, I think. I've seen some projects here in Wisconsin use automatic shading windows, which is a little bit different. It's not quite the same thing as having solar PV in the windows. Most of those technologies right now, they work, they're available, they're a little on the expensive side yet, but I'm hoping that'll come down over time.
And a question from Rebecca asks that you primarily focused on residential and commercial buildings. How are energy performance strategies different for industrial buildings, or are they similar to commercial buildings?
So yeah, great question. Industrial buildings, the primary energy usage is usually in what they call the process load. So the process load, for example, in, I don't know, a canning factory is in, the canning. Or in a paper factory, it's in the making of the paper, or in a foundry, it's, the steel. So the process load tends to dominate in the industrial world. The facility itself tends to be a bit of an afterthought in industrial situations for that very reason. However, there are things they can do, especially with their lighting. There's usually a lot of lighting load in industrial facilities that can be, and we've gotten amazing technology jumps in lighting. So that's an easy win for most industrial facilities. But yeah, industrial facilities are process load dominated. So their focus in terms of making improvements is usually in analyzing their process, whatever it is they're making, and seeing if there's efficiencies they can drive in their actual process.
Great. Any more questions in the room here? I think we've addressed all the questions. Thank you so much. Oh, I guess we do have one more question here in the chat.
Okay.
Yeah. So Todd is trying to get you to force an answer here on PVs versus green roofs. If you're forced to choose which best reduces the building's carbon footprint.
Oh, that's a hard one. I had to choose. Probably if your building's in a location where you're using what I'd call dirty electric grid, then I'd go for the PV to offset that. If you're building a house in Vermont where you got the cleanest grid in America, go for the green roof. There's a lot of factors that go into that decision. So it's not a straightforward answer.
I know that the Milwaukee Public Library has both on their rooftop.
Yeah. Well, that's a strategy. You can split the difference so that, if you have a accessible green roof that people can go up and wander around, put some PV up there too so they can see that and, and learn from the solar production as well. So.
Great. Well, I think we're at time. So this is a great spot to end. Thank you so much for your presentation today.
Thank you. Sorry I couldn't be there in person, but believe me, you wouldn't want me there today.
All right. Yeah, this has been a great overview of energy efficiency. So thank you so much.
Thank you. Thanks, everyone.
Have a good day.
Thanks.